Okay, now we want to look at the effect of doubling or halving the increment. Okay, so we have the function, it's the y equals x cubed plus 5 function on the interval from 0 to 1.5 here. Now, if we double the increment, then we're going to have an increment of 0.2, and we're not going to hit 1.5. So we're just going to do this for x values 1, 1.2, and 1.4. And I don't bother calculating the y values. They're already there on the original table for this function. Now that table's been extended here, but I leave it to you. You can very easily do these calculations, especially if you can use Excel and cell references. It makes it very efficient to do these sort of calculations for tables of reasonable size. Okay, so I'm just going to go ahead and list the slopes that we get at these points. Now this is the slope for the interval from 1 to 1.2. It's the average slope. It's the slope of the trapezoid on that interval. Now let me do a sketch over here to kind of give us a little more perspective. Okay, I'm actually using a little color coding here. I think you can see this is yellow. And this is just a rough picture of our original graph. The increment was 0.1. I've labeled 1, 1.2, and 1.4, but of course we have 1.1, 1.3, and 1.5 here. Now the 1.5 occurred on the original graph. It's not going to occur on this approximation. On this approximation, we're just calculating the values here, here, and here at 1, 1.2, and 1.4. So that we have this trapezoidal approximation in purple. And we can see that this approximation actually goes over the top of our previous approximation, or at least it would if I'd have drawn this approximating segment a little more accurately. Now, when we construct that graph, again, I'm not going to go through the calculations. I just observe that these are our slopes, 3.65 and 5.08. 3.65 here, 5.08 here, compared to our 3.31 and 3.97 that we get here and here, or our 4.69 and 5.47 that we got here and here with our original graph. And it's going to turn out that since these increments are equal, that this average slope will be the average of these two, and this average will be the average of these two. And you probably want to check me on that last statement. Okay, now we also get the accumulated areas, and then we compare with the derivative at the midpoint and the accumulated, or the change in the antiderivative, and so forth, and we get our discrepancies much like the discrepancies we've got up here. Now let me circle a couple of things. Now these are the discrepancies between the slopes of our trapezoidal graph and our actual slopes, and here are the discrepancies between the accumulated areas, the trapezoid accumulated areas, and the actual accumulated areas that we would expect from the ideal, the perfect function. Now, these discrepancies, how do they compare with these discrepancies? Well, one thing is I've still got those pesky negative signs on them, so let me get rid of that. Okay, the discrepancies here are 0.01. They're both the same, just as they were always all the same here. But what happened to the discrepancy? Now, let's think about it. We doubled our increment, so we're jumping over twice as much of the actual graph with these increments. How does that affect our discrepancies in the slopes? Well, it appears, and you should be able to do this just visually, and you should not by any means have to reach for a calculator to see this, that these numbers are 4 times as great as these. And if you don't see that, you really need to make yourself do a lot more mental arithmetic and think about the numbers so that you can see these things without having to resort to machinery. That's a very simple, some of these other comparisons are more difficult, of course, and sometimes you do need the machinery and you need to know how to use it. Okay, discrepancies here. Now, how do these discrepancies compare with these? Well, 0.004 is about 8 times as big as 0.0005. So this discrepancy is about 8 times as great as this one. And well, it might be more appropriate to compare it with this one, where it's about 4 times as great. But then here we have between like 4 and 6 times as great a discrepancy. So the discrepancies get much larger. Might be expected by doubling the increment, you would double the discrepancies. Now let's just make sure we understand why there are discrepancies. Okay, there are discrepancies simply because of the curvature of the graph relative to the straight line, and then some more subtle discrepancies because of the nature of the curvature. When we make the increment twice as big, both of these discrepancies get more than twice as great, and in fact this one gets 4 times as great, and this one appears to get even more than 4 times as great. Now we list similar values, but now for a trapezoidal approximation graph with a step of 0.05, half the increment we used on the original, and we want to compare these discrepancies with the discrepancies in the original. And let me just sketch what this means. Okay, now our original increments of 0.1, which would be from here to here, 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 have each been cut in half, so the increment is now 0.05. And our slope segments, our approximating segments, are going to be much closer than they were for either of the other 2 increments to the actual curve. So we're going to be getting much closer to the actual curve in a way that makes our slope approximations much more accurate and our area approximations much more accurate. Now, in listing the quantities down here, I haven't listed every quantity. Okay, I've listed the slope between 1.05 and 1.1. Okay, that would, for example, be the slope of this trapezoid. I've skipped this trapezoid from 1.1 to 1.15, and then I listed the trapezoid from 1.15 to 1.2. I've listed slope, accumulated area, and so forth. So I'm only listing the quantities for every other trapezoid, but all the other quantities have actually also been calculated. So even though I'm only listing the results for trapezoids that appear to be 1/10 of a unit, 0.1 unit apart like these, the results actually apply to just the smaller trapezoid of width 0.05. And just for the sake of saving space, I've omitted all those others. Now, most of the time I put dotted lines in there, dotted, 3 dots and ellipses to indicate that there's a missing value on each of these. Okay, so they've all been calculated, but I'm only representing every other one. Okay, now, when we do this, here are our slopes, here are our midpoint slopes for the actual y prime function. Okay, same columns that we had up here, so I didn't relabel them down here, running out of space and having to write about as small as I can get away with and still be reasonably legible. And the accumulated areas and the y function, the capital Y function, the accumulated area function, and then the discrepancies. And I just note, I think I've reversed these 2, so let me fix that. Okay, seems like this is one of those places where I thought I might have made a mistake but didn't. I did include the TAG label here. So these are the accumulated areas of the trapezoidal graph, and these are the accumulated areas as calculated by the accurate antiderivative function. And that just continues down, so we just subtract these numbers here and we get the discrepancies. Actually, these numbers, differences in these numbers, give us the slope discrepancies. These are the slopes, and these are the accumulated areas. So here are the accumulated area discrepancies. Now let's see what the comparison is. Look at it and see what you think before I say anything. Okay, well, okay, first of all, we would compare our slope discrepancies with the slope discrepancies from this graph. So I would bring this arrow down here so that these numbers would be now compared with these, and bring this arrow down here, so that these numbers would be compared with these, the area discrepancies. So what happens? The slope discrepancies now, where they were 0.0025, when we cut the interval in half, the increment in half, we get a slope that actually is 1/4 of what it was. So what happens if we double the increment? We increase the discrepancy by a factor of 4. If we cut the increment in half, we decrease by a factor of 4. So that as far as estimating slopes, it appears that every time we cut the interval in half, we quadruple, or in terminology you might be familiar with, fourple, the accuracy. Okay, and we reciprocal or cut the discrepancy by a factor of 4. With the areas, what happens? Well, let's see. If we compare the 0.0013 with the 0.0052, we see that that's about 1/4 of this. That the 0.0027 is about 1/4 of this. 25 is 1/4 of 100. 27 is 1/4 of 108. So that 1/4 seems to work pretty well. But when we get down here, we get a 0.0006, which would be like 1/5 of this, but 1/4 of this. So it looks like we're tending to improve the accuracy of our area increments by a factor of at least 4. So it appears that cutting our increment in half, increment or step size in half, appears to fourple our accuracy. Okay, if we start here with an increment of, or step size of 0.2, our accuracy would be like, our discrepancies would be like 0.01, whereas up here they go down to 0.0025. Our discrepancies here, well, between here and here we have the increment again, and we get another reciprocal fourpling. We get 4 times the accuracy. Now, it appears that we get a little better than 4 times the accuracy each time we cut the increment in half, as we're estimating the accumulated areas, the area under the curve. Now, this is not a hard and fast thing. I say, for example, we go from 1 part in 1,000 to 1 part in 4,000. There are all kinds of qualifications here. That figure obviously changes from 1 in 1,000 here to 1 about 2,000 here, and it's not consistent, completely consistent over the areas either. But you get the idea that every time we cut the increment in half, things get a lot more accurate, more than twice as accurate. It appears at least 4 times as accurate.